So it's all about centroids today. Okay. Okay, are you good with the theory, perhaps? So we can do more examples. Okay.
Maybe just go a bit through the theory.
So just a bit, okay.
Yeah.
Okay, centroids and distributed forces. So basically what they're saying here is that when it comes to distributed forces, this is basically all about how the forces are acting on an object. It might be in a line, it might be on some sort of surface area, or it can be on in terms of 3D now. When you have a liquid, let's say which is in a pipe which is under pressure. So there will be forces acting from all the excess. Okay, so what they're saying about distributed forces is that forces applied over a region whose dimensions are not negligible compared to other pertinent dimensions. So this when it comes to distribution of forces, so what you would want to know now, what is the total force which is applied on the entire surface of that object, whatever it may be, even if it's a line or it's some sort of a two-dimensional surface, or it's like a three-dimensional surface whereby you have forces from all the three axes. So what you need to do now is you need to do some sort of you need to total or you need to sum up all those forces so that you can get the total force acting on the surface of that object. So so for some shapes that you know the formula for calculating the surface area already, or the volume, that formula, or the length. If it's a known shape, if it's a regular shape, the formulas are known already. But you can always derive them also if you forgot. Okay, so this is when now your integration comes in. In your math, you have done with integration already by now, isn't it?
Yes, sir.
Oh, okay. Yeah, so you will be an expert actually. It has been a while ever since I did some of these things. So that's why here they are saying summing via mathematical integration. So you want to sum them up so that you can find how many of them, like the total force acting on the entire surface. Okay, so in terms of the line, normally what you determine is it's like a force which is let's say this force here acting at this specific point or on the line now. So if those forces are a lot acting on over a longer, let's say along the line, long line, so you're gonna have to find the total force over the distance divided in which those forces are applied. And if it's over an area, like a two-dimensional area, so you're gonna have to find the surface area on where the forces are applied. And if it's a three-dimensional object, you're gonna have to find the volume along which the force is applied. That's why now for area, your formula, your unit will become like newtons per square meter, while for volume, it's going to become newtons per cubic meter. So that's why, okay, so it's all about studying how those forces are distributed along the object. Again, if you come here again, a similar thing again, I think here they're just demonstrating how you can actually determine the center of gravity. Here, the center of gravity of an object. And by the look of things, it's like there are two methods that you can do it. You can do it by doing some experiments. You can have that object hanging, and you shift it like that. You can see it will still be, if it will remain stationary or it will be remain rotating like that, so that you can see where the center of mass is almost lying. While on this side, or you can actually do it by making use of the principle of moments. This is now where your integration, all your mathematics comes in. Most of the time for tests you'll be using this, but for experiments maybe, but I'm not so sure if you guys did experiments on this maybe. It's most
We did not.
You did it.
I know we did not do it.
Yeah, nonetheless, yeah, I think most of the time they focus more on this calculation of moments. Okay, so again, just like on the other side, in terms of the distribution of forces, the principle of moments again is a summation of moments. So you're gonna sum all the moments acting on that object. So, and again, if it's a line, like on the other side, if you remember on the other side, what we said here, if it's for a line, Newton per meter. For area, it's Newton per square meter. Its volume, Newton per cubic meter. Again, in terms of moments, you can find your force up here like that. Then you divide it by the distance now. So you have your force here acting on it. Your force times your, this is like the force, and this portion is the dm. It's like the small distance that is removed divided by the distance now. It's basically the same as at the top. You basically have a moment that you have the force times distance, force times perpendicular distance, times divided by the distance here. Okay, again a similar thing here. This is now in terms of weight. This one is in terms of, is like weighted. Okay, and again here. Okay, here now it's in terms of the centroids now. So basically a centroid, to me, the way I see it, the centroid is like, you do not say it's like a center of mass, isn't it?
Yes.
Yeah. So they say here, center of mass position. This is what you'll be calculating. You'll be calculating the center of mass position. Now, depending on by making use of these three axes, x-axis, y-axis, and z-axis. So you'll be using all those three to calculate your center of mass, mainly by applying the principles of integration. If it's on the line, and you are doing it along the x-axis, let's say the x centroid, you'll be dividing, you'll be multiplying that force now times the length divided by the length of that line. Same if it's on the y-axis. I think these components of x, y, z, these ones, I think sometimes you even get them from, I'm not sure if you get some of them from a table also. If I can recall well, there used to be some sort of table where you get some of these values, especially the equation that you might use. Okay, so this is for the line. For the area, you will basically be dividing by the area, and you will have a small area here. Small area that it's like you are basically moving a small area along an object. Let's say now you have your object that looks like the object looks like, let's say it looks like this, and then this is the, let's say this is your y-axis, this is your y-axis, this is your x-axis, this is your x-axis. So you're gonna have to take, let's say, a small piece of that. It's like a strip. You're gonna take a small strip like this, and then this small shape, you're gonna have to move it along. Because here you know already the distance from here is, let's say y, let's say h here, from the bottom here to the top there is h. You know already from here to, let's say here, from here it's a small change in x. So they usually name it like dx. While from here to here, they can say it's like x also. So what is happening is this small portion here is the one which is the one that you see here. Let's say if it's dl, if it's a line, you can say it's a small line. If it's an area, it's like a small area along. It's an area of this small piece. So like this area here, it will be like it's a small piece, isn't it? So you're gonna say dA, like an area for the small piece. So that area, since this looks like a triangle, for a normal, not a triangle, I mean like a rectangle. I can make it nicely straight. Because for the normal rectangle, you usually say length times breadth. So your length can be this h, for example. You can say it's h, and the breadth is like the width. It's like this dx. It becomes that dx. That small change. You see. So that's why now it depends again. If let's say this becomes 3D, let's say there's another z-axis here, z-axis. If there's a z-axis there, then let's say this becomes a 3-dimensional object, something like that. Then it means this object will be 3-dimensional. So it means now there will be another component. Let's say this portion, this side. So then let's say we name it dz, something like that. If it's like that, then here what you're going to have to compute is the volume of this object. You're going to have to compute the volume. So you're going to have dv equal to this area already times this small width, or this small width again, so it becomes dz. So instead, this dv is what you see here, what they have here is the volume there. And this dv, it's more or less the same as this, except this one, the one at the denominator, is for the whole object already. Let's say, especially if you know the shape of the object, if it's a regular shape, then you just use that formula, like length times breadth times height straight. But with the top part, this portion, you're going to have to integrate to get that portion. So basically, most of the questions that you might get regarding centroids, they will only ask you, let's say, to calculate the x centroid. If it's x centroid, let's say you are given a line, then it means you're going to use this equation. If it's, let's say, y centroid for the area, it will be this equation that you're going to use. Like that. If it's a volume, then depending on where they want, on which axis they want you to use. Sometimes they might not specify. So in certain cases, you might need to depend on your inspection. You just need to see how the object is aligned. And then based on that, you can deduce that this specific axis is 0 here, or like that. Then you can remove some of them. Are we good up to date?
Yes.
Okay. Okay, now here, in terms of the choice of element of integration, what they mean here is that small piece, let's say this small piece that you're gonna use to integrate, like this one is a vertical one, okay? And again, this small one here is again a horizontal one. But the most important thing is that it's a first order horizontal element. Basically what they mean is, if you look at that equation, if you are to come up with this equation for this, when you're integrating, let's say the area for this horizontal piece, okay, the area for this small horizontal piece, you can assume that, let's say, the horizontal, its length from here to here, it's, let's say, x, isn't it? But the width is this, the width is dy. So its area, because it's a small piece, you can say dA. dA will be equal to x, which is the length, times the breadth, which is the dy. So basically, what's going to happen is you will let me just put it here. So now the area of this object, of this horizontal piece, to be, because it's a small area, it's a small change, it's a small change in the area. So it's a portion of the entire object, of the entire shape. So the area, normally the area of it's like a rectangle. So if it's a rectangle, your area is length times breadth, isn't it?
Yes.
So in this case, your length is this on the horizontal. In this case, is like x. Okay, while the breadth on this object, or for this object, is, it will be this small portion which is cut off, which is dy. So even if you are solving your ordinary, in terms of differential equation, this is the ordinary differential equation. It's like a first order or first degree differential equation. Even if you have to integrate, you just integrate. It's simple one. It's those first order ones. It's much easier to integrate those ones. So what they are saying here is, when you are choosing the portion, that small area that you will be integrating with, that element that you'll be integrating with, you need to choose an element. Whenever possible, you need to focus on first order differential element, the one that will give you first order equation. You need to choose, by all means, to take that one. Okay, that's in preference to other higher orders, like this one here. This is a second order element. It's a second order because if this looks like a square, okay, If you say again left times, let's say like length times breadth, you say this will become dx times dy. It will become dx dy. So you're gonna have to integrate twice if you have to do it, which makes things more complicated. You see? And if it was, let's say, three-dimensional, then you have three of them again: dx times dy times dez. Then that's third order again. So which is making it more difficult again. So they always opt for first order equations. And again, what they're saying is continuity. One continuous operation is preferred over two. So in short, you don't want to, let's say if you take this small piece here, this small vertical piece, you can just integrate from here to here once off. But if you have a shape which looks like, let's say like this, or maybe some other funny shapes, it might be difficult for you to integrate. Let's say when you are here, for example, when you are here, this entire region is somehow not covered. Imagine now if there was a small piece going like that, so it might make things difficult. So if it's possible, all they're saying is get one element that you can just move around like that once off when you're integrating. It's just to avoid complications with integration. Otherwise, you'll be doing a lot of integration by parts and all those other things. Okay, so the higher elements also they have issues of coming up with errors. There's a high chance of coming up with errors. Remember, this whole thing is it's more of an estimation. If you look at this one, for example, there's a small piece here. So this small piece that looks like a triangle, it becomes a high order element, that one. Because you will be having this portion here, it's a small portion over the x-axis. So it's the x at the bottom here. And then on this side, you have dy. So that's why you have dx dy. And this 0.5, it's because it's a triangle. You understand that? Do you understand that part?
Just quickly, just explain.
Okay, let me just put it here. What we have, it's a, okay, you see this shape here? I'm gonna put it on the other side. I'll just draw it quickly here. You have something like, it looks like, okay, that goes like that. And then, okay, this is your x-axis. I mean your y-axis. This is your x-axis. Okay, let's say now here you are integrating this small element that we took from here to here. Okay, you see this portion from here, this small portion, this area here. How would you? What will be the dimensions of this area? The length here. It will be a small
This
change.
is now the dx.
Dx, ne? Yes, it will be dx. Because it's a small change on this axis. Okay, now there's a small portion at the top here that looks like a triangle. This small portion here. Okay, so this small portion is having this length, yeah, like the length of dx. Okay, but in terms of the height, let's say that height is coming from here to here, like that. This small portion, the length for this one, it's a small portion coming from this side. So the height here, it will be dy, isn't it? Okay, so basically what we have is a shape that looks a bit like that. Looks like that. But if you look at it well, it's like it looks like it's a triangle. If you look at it well, it's like it's a triangle like that. You see, but there's a small portion which is not, which is here, It is like an arc to the corner there. So it's a triangle which is having dx at the bottom here, the dimension on this side, dx, and on this side you have dy. So now, when you're finding the area for the triangle is usually half base times height, isn't it?
Yes.
Okay, so if that is the case, in this case now, this small area, which is d, I can say dA, it's like a small one, is equal to half again, instead of b, the breadth, I'm gonna have dx there, and the height will be dy, gonna be dy. Okay, so this equation itself, this equation, it's a high order differential equation. It's a high, yeah, it's high order element, this one, because you have this both dx and dy. That's what they are saying here, 0.5 dx dy, 0.5 times dx dy. So that's why they're saying ignore this high order element. So it's gonna give you problems if you're gonna do that one. So you just consider it like as if you're cutting it off with its origin. Because apparently what they're saying is that if you to ignore it, it's just a negligible error. It's a slight small error that you can live with. Okay, and again, okay, and again, if you have an arc, if you are given an arc, you normally choose, again, you choose to a shape that you can easily rotate around this arc. Like this small portion that you see here, this small portion here, you can easily move it around from this angle, from an angle of, let's say 0 degrees here to, let's say, I don't know, maybe 75%, 75 degrees, you can move it around there. So when you're integrating from this point of 0 to that point, from using that angle. So you need to choose what best matches the boundary, this boundary here along. So this shape again, you're gonna look at it more of like a triangle that you will have there. But it looks like a triangle, but it's having a small arc on this side. And this is where now you need to remember what you did when you were doing did you do those things of calculating the arc length? Did you do those things, calculating arc length?
Yes, sir.
Yes, yes. You can apply such things. Okay, and again, the same calculations will be used again when you're calculating now the centroid coordinate elements. Okay, and again here what they're saying is the centroid coordinate elements. So you see here, x bar, y bar, z bar. These are coordinates. What you're trying to do is to locate the center of mass of that object along those three axes. So you need to find those coordinates. That's what they are always asking for. Okay, so it's not far from what we discussed previously. It's just the shape that changed. Otherwise, everything else is the same. Even these formulas, they are more or less the same. Actually, that's the same exactly. Okay, we can look at this example. Example now, for example 1 in here. So what they are saying is determine the location of the centroid. Determine the location of the centroid. The centroid of a circular arc. Okay, you see, this is a circular arc that they are talking about. Okay, so that's a circular arc that you need to find. Okay, okay, the shape is initially looking like that. Okay, you see where this point is. This is like an assumption just by looking with your eyes where you think the center of mass will be. It will be somewhere in the middle, like it's a mirror where where you can put a mirror for both sides. So if you have to do that, it means that this point will lie on the x-axis. So if it has to lie on the x-axis, it means now just by doing that inspection, you have actually concluded already that that y bar is equal to 0. Same as x bar, just that x bar is not here also. Okay, so let us, okay, so the other thing again, okay, what you need to do now is this small element here, it's the same example as we did in here. You see this small piece here, which is forming the arc, is the one that you should use in your calculations. And again, when you are doing this, you're gonna have something like you're gonna have a shape that looks like this. Okay, where this arcos phi is coming from, if you look here, this shape, you have something like a triangle, looks like a triangle like that, but then here at the tip it's like this. Okay, you can think of it as if it's a triangle. It's a triangle. Then here you have your angle. Let's say you have your right angle there, just for illustration. So the angle that you have here is now your this alpha, this phi alpha, not alpha, but the theta. Okay, but on this side you have your radius on this side, but this side you don't know now. On this side you can say now it's more for the x side that you want to find out now, because here it's more from the x-axis. This dimension is horizontal to the x-axis, isn't it? These are cos. So you can say cos this angle is equal to your adjacent, this x divided by the radius, this portion, the hypotenuse. So your x is gonna be r cos that angle, like that. So this is the portion, this small portion at the top here. Okay, nonetheless, this whole thing, we're gonna have to work like this. So what you need to find now is because what they want you to do is to locate the centroid in the x-axis. Okay, if they want you to do that, then it means you don't have a choice but to use the angle, but to use that one of those formulas that they gave you initially. These formulas we are referring to here. This formula, because you are focusing on x centroid, this x equal to this equation is the one that you're gonna have to use for that question. So what you're gonna have that equation x bar equal to integral c over d times dl, because it's the length. It's a small length that we are focusing on. A small length on the arc, on that arc, divided by l. Okay. So the tricky part is now, all you need to do now is determine these two. You need to determine the denominator and the numerator separately now, and then you just can put them in this equation. So let's do it on this side. Okay, let's start off first with let's say L here. This L here, capital L here, you can say you can derive it from let's say when you were doing this arc, when you're doing those arc calculations, you probably come across, you have done probably something like calculating arc length. Is when you're calculating arc length, so what they probably told you that you make use of the central angle. Central angle divided by the degrees for the circle, 360 degrees, the entire circle, times this, it's like the circumference, I think it's like 2 pi r, if I can recall these things, 2 pi r. So for this, for this circle, the angle that we were dealing with is that angle of it's because that angle is 2. You see the angle that we are dealing with here for the whole thing. The angle that we are dealing with here, because the capital L, ne? You see this capital L that we are dealing with here is the length for the whole thing from here to here. So it's the angle that you're working with here is the angle for the whole thing. So it's this angle alpha and also the alpha on this side. So it's alpha plus alpha. So it's alpha plus alpha. So you're going to have 2 alpha there. You will have 2 alpha divided by. Normally these things are done in terms of radians, isn't it?
Yes, sir.
So if it's in radians, then it's going to become 360 is the same as 2 pi. Because pi is like 180. That one is never forget that one. Times this same. Okay. The circumference 2 pi r. Okay. This 2 pi will cancel with this 2 pi. Then you're left with 2 pi r. Okay. You're left with 2 pi r. Okay. This 2 pi r is the arc length. That long arc. The entire arc is having the length of 2 pi r. And it's also equal to that L that you were looking for. You see? So we found that this portion, just like that. Okay, so now the other portion now, so we found the denominator already. So the next thing we need to find is the numerator. The numerator, we can find the numerator by first calculating the small arc. The small arc, this small portion of the equation GL. The small arc that they are referring to is this portion here. This portion here. Where did they do it? Yeah, they did it here. They showed it here, but they're not really sure how they came to this number. Okay, the small arc is this small portion here. Okay, the other calculation, L, capital L, is this whole long journey, the entire arc, the length of it. Okay, so for us to find this small arc, it's a similar concept again. You're gonna have to use the similar thing because both of them are arcs, except that one is a small one. Okay, so one thing that you need to know, remember, we're gonna still use this same equation, the angle again. Remember, previously we used alpha plus alpha, so we're using 2 alpha. In this case, the angle is is this alpha d theta? So we're gonna have to use that d theta. So again, you're gonna have to use the same equation, arc length. In this case, we can is the same equation, eh? In this case, we can just say, instead of saying arc length, because we know it's that small portion, we can just say it's dl, because it's this portion of the equation that we're working on. dl is equal to center of the central angle. In this case, it is what is it? D theta. Okay, so that one divided by again. Let's just say 360 2 pi times 2 pi r the perimeter circumference. Okay, then this guy will cancel with this guy. Once those two will cancel each other, then you're left with r d theta, like that. This portion. So now we know this dl and we know l. So basically, we can actually substitute them into this equation. Okay, we can substitute them into this equation. Then it means you're gonna end up having. Okay, the other thing again, you see this x. I've shown you how we got x on the other side. Do you remember how we got this?
The X.
Okay, because that was just like a triangle, ne? It was like a triangle that looked like that.
Oh yeah.
It was having an angle here. Here there was r. Then here I think we said x is here. Okay, so this is that other small portion. So then we use cos that angle is equal to x over r. Okay, therefore this ends up giving us x is equal to r cos theta. Okay, so it means now in this case we can actually substitute x. We can substitute x here. This will be your x c, a small c here. This will be your xc. This gl, we know gl is this one here. Okay, and then we know L alone, we know it is this one. So we can actually just substitute this into this, and then we integrate. So here again, you have the integral sign. X is r cos theta, Then GL is this portion here. The R, let me just say times R. Okay, this is R d5. R d5 divided by L. L gave us 2, 2, 5, 2 alpha R. 2 alpha R. 2 alpha R. Like that. Okay. So with this, okay, I can clear this out, isn't it? Okay.
Yes, sir.
Let's see how it looks like that. Okay, you can substitute in here. Okay, in here, R, the R's can cancel each other. R can cancel R, and then okay, that's it. Okay, then you're left with okay, there's still one R at the top there. Then you're left with R here divided by 2 alpha, okay, 2 alpha. Then here is your integral sign. And you're left with cos. This is a term that you are integrating with respect to this theta, d theta. Okay, so you're integrating this now. And you need to integrate this now from V here to here. Because these two angles are the same, this alpha and alpha on this side. So this alpha on this side, if you look into in terms of the quadrants, this will be negative alpha. This will be positive alpha. So it's coming from negative alpha to positive alpha like that. I think they say, what did they, yeah, like here, what they're saying here. Okay, how to mention it even then alpha. Okay, so now, okay, integrate this from minus alpha to positive alpha like that. So if you integrate that, you should get something like r squared r over 2 alpha. Then that cos will become sin, should become sin normally. Then this the ranges you can put them outside again with that like that. Okay, then you integrate. Okay, then you do your integration to alpha. Okay, this will become your sin alpha minus, because this one is also having a minus, then it becomes minus sin alpha, not alpha sin. Try again like that. Okay, so now what? Okay, so now you can add them up. Okay, this will become positive, so it becomes a plus. So if sin plus sin, this becomes 2 sin. So this will become R2 alpha times 2 sin 2 sin alpha, 2 sin alpha like that. And then you these two we're gonna have to these two we're gonna have to these two we're gonna cancel with these two. And then like that you are left with this r over alpha sin in alpha. It's a solution. This should be a solution, I think, in terms of, yeah. But if you, yeah, because but here you remember you have used radians here. Yeah, we have converted everything to radians, so maybe that should also be in radians. Otherwise, you're gonna have to convert it back again. Okay, if you can check, what did I get here? R sin alpha over alpha. So it's the same. So you got exactly the same answer as we got here. Okay, were you able to prove to do this? You were able to do this, isn't it?
Yes, sir.
Oh, okay, no, that's good. Okay, let me just erase this. Okay, then it's fine. We don't need to prove the ones underneath them. So what did it say here? Say something about proving. Okay, okay, okay. Then you should be able to prove that alpha, if alpha is pi over 2, 180 is like 90 degrees. It's you get your x bar is equal to this. I think this should be easy because you have, if you are able to prove to come up with the equation here, then this should be the easy part. I think we can move on to the next one, isn't it?
Yes.
Did you solve it? I'm not sure if, I'm not sure if I'm doing it exactly the same way as you guys were taught maybe in class. Is it similar to that?
That's it. Similar.
Oh, okay. The next one is about okay, the next one. Okay, it's about this what is this? Parabolic length, parabola. Okay. Determine the location of the centroid of the parabolic length shown below. Okay. From x is equal to 0 to x is equal to 6. Okay. From there to there. Okay. Should be somewhere around there. Okay. Okay. So what they've done is they've come up with this equation. Okay. So they're saying is again, in this case again, what you are proving again here is the equation of the parabola that you are working on here. This is more of a two-dimensional object. Therefore, you have to find, yeah, yes, a, I'm just on phone. Oh, okay, okay, I'll get back to you. I can back to the I'll open. Okay. This will be the only two main changes. Okay, so okay, you can see this drawing, right?
Yes, sir.
Okay, were you able to come up with this first equation?
No, sir.
Okay, it's basically what you have here is this. You have a small, it's like a small triangle there. You have a parabola, like the axis. So this is your y axis, and your x axis. Like x and y. Okay, it looks like a shape going like that. Okay. You can take a small piece here, like that. Okay, so now what you should do is now remember now this small piece here that you have here, because this small piece which is coming on this side down here, its length, the length of this small piece is like in terms of x-axis. It's in terms of x, so you will have a small change in x here, the x, the dimension in the on the horizontal here. While on the vertical here, it's cutting from here, isn't it?
Yes, sir.
Cutting from the y-axis like that. So it will be dy, just like in the other example that we did. Okay. Okay. So
So quickly, what is L again?
L is like the length. It's like the arc. You can say it's like the arc length.
Oh.
What did they say? This here, parabolic length. It's basically length. If you can say. It
Oh.
depends now. If it's like a circular thingy, it becomes like an arc. If it's just something shape like this, you can just call it length. At the end of the day, just length. Okay.
Oh.
What I'm trying to do is show you this. Okay. So now that L now, this is a small change now in terms of the length of the parabola, the small length that you are working on. So this is now your DL.
Yeah.
And remember again, the whole shape from here, if you follow the entire line now, this whole line, the whole line becomes L, isn't it?
Yes, sir.
The whole line is L. But this small portion, the one that you are dealing with, that you are trying to integrate, this small portion here of that line is DL. It's a small L. Okay, this small portion is a small L. So in this case now, if you were to apply your Pythagoras theorem, this is a triangle most.
Yes.
Right angle here. Okay. If you were to apply your Pythagoras theorem, you end up saying dl squared here equal to dx, this whole component again, squared plus dy squared, isn't it?
Yes, sir.
Because it's like a triangle. Therefore,
Yes.
dl is equal to square root of squared dx squared plus dy squared, square root of that. That's how they came up. I think maybe that's how they come up with this. Because even if you look into this, this is a small triangle that I have shown you there. Okay, so once you have come up with that, that alone, you've actually done a step already. Remember, this DL is this portion here. That DL is this portion. But still, this portion here, we need to write it in terms of the, what is the equation here? We need to write this equation in terms of the equation which is given here now. That x is equal to, the equation given is that x is equal to 3y squared. 3y squared. We need to write it in terms of this and not this. Okay. Okay. I'm gonna remove this. No?
Yes, sir.
Okay. Actually, thought this Zoom will stop itself after some time. How does this thing work? Okay. So what you're gonna do is this equation. If you try here multiplying, you see this. Okay, let me just leave it this way. I'll bring it down here. Dx squared plus dy squared. Okay, because now remember that equation, this equation that I was having here was x is equal to 3y squared. We need to write this in terms of this dx dy, so that you will be able to put this equation into this equation for dl. So in such a way that we represent dl by using the values for the equation given for the parabola. So for us to do that, what we have to do is we need to now differentiate. We can actually just do it on both sides. Like on this side, we can just say dx by dy. Okay, on that side, you can just do it even on that side once off like that. This comes down that 3 times y, 3 times this 2, you bring it down, 3 times 2, y, 2 minus 1, you left with 1 there. So this should give us something like 6y. Okay, this 6y is equal to this. So we need to put this now, this dx squared plus dy squared, we need to write it in terms of dx over dy, like that. And once you are able to put it in this format, only then you can start using this 6y. Okay, so for us to do that, we can do something like you can, let's say, multiply this. You can put d, because remember you are already having dx here, dx squared. Okay, if we can put dy, okay, if you can end up with something like dx squared over dy squared, then there's a chance that we can actually put this inside. So for you to do that, you can actually just put in something like dy. You can put in 2 dy's because you don't need to change the thing. Eh? Just say 2 dy over dy. This is the same as 1 most, because this can divide with this, then it becomes 1, isn't it? Are you with me? Broken.
Yes, sir.
Okay. Then if we square it, it will still remain the same because both of them are squared. They can actually cancel each other out. Okay. Even if you square it, it can still work. But again, if you have to put this squared inside, it will be a problem again because there's a square root here. Then again, then perhaps we should need to put up a square root. Let's say you put up a square root like that. Okay. Now we can actually put this. This can actually go inside now. So what's going to happen is we're going to push. The only one that we need to go inside here is the denominator, so that you can end up dividing here. If you have to put the denominator inside the square root you have already, okay, so it will just become. Then you can actually just multiply them straight. You're going to end up with dx squared. And because this guy here, the denominator, is having a square root already, it will also go inside, then it's going to divide here, dy squared, okay, plus this guy can also be divided by dy squared over dy squared again here. Okay, and this whole thing is you put it inside the square root, but outside here, this component here of square root dy squared. But if you look at this square root dy squared, you can actually cancel off this. This square root can actually cancel off with these two. And then you're only left with dy outside. So if you do it like that, then you can actually be left with dy here. It can actually remain like that. And if you have it like that, the next thing you can do now is this. It's having dx squared over dy squared. It's still not yet here. So you can actually put this as dx over dy, then you put bracket and 2 and square root of 2 outside. You get that point? You get me here? What I meant? Brooklyn? 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 Brooklyn, are you with me?
So my computer,
Oh, it's freezing.
it's flashing. I don't know what's going on.
Uh, okay, but what did I miss? What did I leave you? Is it when I was explaining here?
I just a bit up, so
You heard that?
just one step up.
Oh, okay. So, okay, this portion here. Okay, so what I did here was, you see this, okay? Okay, you saw when I moved this dy squared inside me. Do you see that point?
Also, just a bit big.
Okay. Okay, let me do that step. Okay, okay, here you understand me.
Yes, sir.
Okay, so what I did is I want to put these whole equations inside this dx dy. I want to put them in this format of dx over dy. So the best way I can do that is by pushing this dy squared here, this with the square root. I need to push it inside the square root.
Yes, sir.
Once if I put it inside the square root, this whole thing becomes dx squared divided by this dy dx dy squared plus again dy squared over dy squared like that. Then this whole thing you can put under square root. But again, there is this small portion now of square root of dy squared. This one will be left behind outside dy squared. This square root can cancel with these two, isn't it?
Yes, sir.
So if those two can cancel, then it means outside here, you can actually just have dy. Outside here, you can actually just have dy there. Okay, and again, now from there, this portion again, because both of them, dx and also dy, they are all squared, I can actually put the square root outside. If I put the square root outside, then it means I will have exactly this equation. Then that's why I've done that, like you see here. And then this one, these two can actually cancel each other. Can cancel dy squared can cancel with dy squared, and then you are left with one here. Then like that, you can put up the square root times back again like that. Okay. And then once you have that, means now uh, inside here you can put this y. You can substitute 6y inside 6y. Okay. Square root here plus 1 like that dy. So something like that. Then if you this can become now 36y squared 36y squared plus 1. Then you put up the square root dy is outside the square root. So you end up with something like that. And then after that, you're gonna have to do the what is this? Okay, this one. DL like that. DL. Yeah, you see this one here now. That. Okay. So now what else did they do? The only thing else that they've done was the okay. Now that's that equation. Now they've integrated it by the look of things here. If you look here, since it's the same thing that we have there, they just integrated this from 0 to 2 pi. Okay. I'm quite sure since you have done your integration soon, I'm quite sure you probably have you'll be better off when it comes to solving this kind of equation. In terms of integration, then you should get that 6.26778. Then in terms of the xl xl x dl,
So the YAL is what now? It's that
it's like still length. The length of this whole
so we worked out the length or what?
Here, yes, it was like the length.
Oh.
Okay, so now this other portion here, basically the same again, because the most important thing is to find this dl, which you found here already. So you just multiply it with this x. X is just the equation that you are having from the graph here. 3y equal this, then you substitute that. Then again you integrate from 0 to square root of 2 again. It will be the same thing that you have computed here, similar thing. Then based on that, you found your two answers now. So basically, you now have the answer. You have this one, you have L, you have calculated L, you have calculated GL, Okay, so it means for both y and z, and for y bar and x bar, you have, for both of them you have L and dl. Okay, and then the next thing you're gonna do is just substituting to on y. On x you have already found that one. On x you have already found this portion at the top, which was in the numerator. So the next thing you're gonna have to do is just substitute. You see this equation? You just substituting that 18 divided by that, so you can get that answer. So this is now your x coordinate now. And then the y side, you can actually just go do this one again. You basically need to put this equation in terms of y, in terms of the y axis, in terms of y. You just need to make y the subject of the formula here. And then where there is x bar here, you put y bar. Okay. And then again here where there is x, you put y. Then again you, and then you later you do something like this again, similar to this, but for y. Let's see, did they do it here? Yeah, you see here, yc, the only thing that has changed here again, y dl. Okay, this equation is still the same, the equation that we derived earlier. Then you put y here. Ah, here you don't even need to make x the subject. Okay. Yeah, you don't need to make x the subject here. Okay. Because in fact you are this integrating with respect to y there. Okay. So everything should be in terms of y. Then you substituting, then yeah, then you get your answer here. So the only issue is finding this one. Maybe integrate. I think the only problem here is the actual integration maybe of this thing. I just need to check it out. It's been a while ever since I did some of these things. You just need to find out how to integrate this, otherwise everything else is on point. Are you fine up to there?
Yes, sir. I'm fine about it.
Oh, okay. Okay, now we can do the other, which other one? Let's go to pages of things. Okay, we can go to this one. Centroids integration examples again. Okay, for this one. For this one, you have, okay, let's start with exercise one. For exercise one, what are they saying? What they're saying is calculate the x and y centroid of the area enclosed by the lines. Okay, and between 0 and 1. X is equal to 0 and 1. Okay, so the area enclosed by between these two lines. Okay, enclosed. Okay, so this area between 0 and 1 here. So where the two lines are intersecting. So they want you to find the center of gravity here in the middle. Somewhere, should be somewhere maybe around there. Okay. So as you can see here, they've taken a small piece that will be moving around to cover the entire area, the enclosed shape. Okay. Again, okay, let's say now for, they want you to find for x and for y. Let's do that. There's something strange about Zoom. Why, when I am using Zoom during the day, it gives me that 40-minute, I can use 45 minutes, and then after that, you have to log in again. But now it's not doing that. Something strange.
So something funny is happening with my computer. If I move my mouse, my screen is flashing. I'm not sure.
Is it? So
Yeah.
maybe you need to move it. If you use the, even if you use the mouse itself, or even if you use the mouse on the laptop itself.
I removed the mouse, the wireless mouse. Now I'm using the pad, but it once if I move it, it's just flashing.
Oh, okay. Okay, but we'll get there soon. Okay, so here, what they want to do, you can see that they've given you this drawing here. You are actually just trying to find the, if you are to move this area now along. Let me just draw it quickly here. It's like that. Okay, nothing like that. one shape that goes like this, then the other one that goes like that. Okay. Okay. So y is working. X side. Oh, it is working. And here is y working. X squared and x equal to y squared. Okay, so what we have here, you want to find the centroid for the x on the x-axis and also on the y-axis. Again, you use similar equations again. X bar equal to your integral sign xc c d. Because now you are using it's an area name that we're talking about, not necessarily the length. Okay, dA over a. Okay, that's the one side of the coin. And then we also asked to calculate y bar. So the equation is bar y c over times dA divided by 8 again. Okay, so these are the two governing equations that we need to find now. Okay, normally what you do is for the shape that is like a regular shape, it's the way you can use area like this because you know the formula is it's given already. Let's say if it was a rectangle, you know already the area of the rectangle is length times breadth. So in this case now you're gonna have to integrate it because this is not a regular shape. So the area you can actually just put the integral sign. You can actually put the integral sign here, then you just integrate that entire area because it's not a regular shape. Okay. So what you can choose to do now, you can choose to move. You can choose an element somewhere. Let's say an element here. Are you following so far?
Yes, I'm.
Okay. You can choose that element. Okay. This is the element that we are going to move around so we can cover up the entire area. Okay. So if this is the area that we're gonna, this is the element that we're gonna move. Okay. This is your x-axis. This is your y-axis on this side. Okay. From here, normally from here, there to where this is where your because it's parallel to the x-axis, so you can say this is your x, and normally this is your xc. Okay, but for the object itself, for the element itself, that dimension, that length, this is your dx. While from here to here, this is now what did they say on the other side? Okay, you can name it in terms of y's, like the first equation, second equation, and that the points. Okay, you can say okay. Since that's what you say y2, y1 here, y1, y1 here. Okay. So what you are having now is now for us to determine the area now. The area of this small piece. That area would be something like okay, we can say it's area here. It's still area here. So it's area, except we are finding it using an integration. Okay, they say it's from 0 to 1. It's from 0 to 1. I think one should be somewhere. One should be here. One should be here, and then here you have 0. So it's this whole thing. Okay. So the area for this thing is your A. Okay. So that area from 0 to 1, that area is you're integrating from A from y1 to y2 like that. So now your dA, you see this dA, this small area, the area of this small piece now. Okay, let me just bring that small element, that small piece here. Okay, that small piece, it's having this is the 8. Okay, this is this is the ending point, y2 here, and the beginning point is y1 that we have here. Okay, so it means now the height of this object, of this small element from here to here, it will be the difference between this and this node. So the height
Yes.
it should be y2 minus y1, because y2 is the highest point, minus y1, like that. Okay, while on the other hand, the the width should be now this point. Okay, this should be now that small piece. This small piece should be your dx. That small thing should be dx. This small point, this small portion here. Okay, therefore your dA, your dA, your dA, which is now area of this small rectangle, area of a rectangle equal to length times breadth, isn't it?
Yes,
Okay. Therefore, in this case, the length you can say is this one. Your length should be y2 minus y1, y2 minus y1 times dx, times dx, like that. Okay. So what it means, so you can actually use this. Okay, so this is the same as your g, is the same as your dA, which you are looking for here. Okay, okay, dA here. So you can actually put that equation here. You say it's equal to y2 minus y1 dx. Okay, so this is what we're gonna integrate 0 to 1. Okay, so now remember this y1, y2, these are equations, right? Equations for this line and equations for this other line. So we're gonna have to put, remember, because we're integrating with respect to x, so we're gonna have to put y2 and y subscript 1 in terms of the equation itself, in terms of x. So we need to substitute that. Therefore, in here, from 1, 0 to 1, okay, y2 equation 2 is this equation here. Okay, if it's this equation, then we need to write this equation by making y the subject of the formula here. Therefore, this should be y is equal to x over x to the power 0.5.
Square.
1 point
Yeah.
half 0.5. Yeah. So this is the equation that we need to put here. We need to put x equal to, let me just put 0.5. Okay. And the y1, y subscript 1, y subscript 1, so this equation here is equal to x squared. Okay. And you have the x outside here. So we put a bracket like that. So we need to integrate this. Okay. We need to integrate this. Now, this is your 0.5 here. Okay. Okay. To 0.5, you just add 1 more. So it becomes 1.5, isn't it?
Yes.
1.5. Then x, this again is 1.5 here. Again, 1.5. Okay. From 0 to 1 minus, this is 2. So it becomes but this 1.5, I think this 1.5 should
It's
have,
over.
this should have been turned around, eh?
I think it's one over 1.5 something.
Yeah, 1 over 1.5.
Yeah.
Okay, then on this side, this should give us a 3. 1 over 3 here. Then, then this will be x to the power 3 at 1, 0 like that. So this should give you, you put your 1 here, this should become 1 over 1.3, because this is the same as 1.5 is the same as 3 over 2. So here it will
Yes.
just become 2 over 3.
2.
To just be inverted, minus, here you end up with 1 over 3. 1 over 3. Okay, if you subtract them, then you should get 1 over 3. This 1 over 3, if you put it on your calculator, it should give you, okay, it should give you 0.3333.
Yes.
0.3333, a lot of them. Units. So this will be unit squared, or whatever dimensions they gave you, the area. Okay, so now, like, so now we have this, the numerator now. I mean the denominator, we have it now. It's 0.3333. That area. So let's see what did you get here? Oh, they got 0.45. Okay, okay, no, it's different. Yeah. Okay, so it's the same. They got the same answer. Okay, so the next thing we're gonna do is compute the upper portion. You see here, in terms of CX, upper portion here. Okay, so we know this, we know this. So we just need to find uh, this the numerator. Okay, so for us to find that numerator again, let me just clear this side. Okay, so now we are doing this one for x. Okay, 0, 1, okay, 2, x, dA. Okay, so now it's similar to what we were doing already, because now remember it's just x. Okay, 0, 1, x will just remain x here. And then remember again here what we're gonna do happen. This dA was equal to this. The same thing that we're gonna put there. Y2 minus y1 dA. 1 dA. Okay. So again, it will be the same thing again. Except now, what's gonna happen is it will look the same as this, except there's x outside. Okay. So you have 0 here, you have 1 here. So x, okay, x 0, 5 minus x to the power 2 dA. Okay, okay, then just put that x inside, so you avoid problems with integration. Then this will become 1, 5, 5 minus x to the power 3 dA. So now, yeah, so now we can just differentiate, integrate nicely again. So we should be able to find that this will become something like 1 over 2 comma 5, just add 1, then x 2 comma 5. So then again it says, let's say, can do 1, 2 minus, okay, 1 over 4, x to the power 4 here, 3, 1, 0, that. Okay, 2.5, this is like it's like 5 over 2.
Yes, around.
Then if you put one here, then this will become, actually, will just end up becoming 2 over 5. You just rotate the inverted 2 over 5. Then minus this side, this one will just become 1 over 4. 1 over 4 here. Okay, so you can actually just do this over, let's say 20, just to find the difference. 5 goes here, 4 times 2, you have 8 here. A 4 goes here, 5 times 1. And then 5 times 1 is 5. 8 minus 5 is 3 over 20. So 3 over 20. Okay, if you want, you can put this 3 over 20 into decimal form. 3 divided by 20 is 0.15. 1, 5. Okay, okay, 0.15. Okay, so here we got, okay, so at the beginning here at the top, we got 0. Okay, this 1 over 3 here for the numerator, for the denominator, for the numerator, we got 0.15. Okay, so we can actually just substitute those two values and we should get our x bar like that. Let's just see if that's what we got here also. Okay, this one 0.15 cubic units. Okay. Yeah, cubic units. Okay. So we can just complete that also. Okay. This one we got 3 over 20. So at the end of the day, this top portion we got 3 over 20, 3 over 20 here, and then at the lower portion we got 1 over 3. 1 over 3. Okay, the same as you having 3 over 20 times 3. So this should be should give you 9 over 20. 9 over 20, that's the same as having 9 divided by 20, 0.45. 0.45. That's the point, the x bar. Okay, 0.45. Let's see what we got. Okay, 0.45. You see, it's the same. Okay, so we got this point. So the next thing we need to do, we need to do the similar thing again. Now for y on y-axis, because now we already know two things. This top portion, we know already this top portion. I mean the denominator. We only know the denominator on this one because the other one we did it with x. So we need to find this one also in terms of y now. Okay. So now, okay, we can do that quickly. We just need to find the one for that y portion. Okay. The denominator to also be from 0 to 1. Okay, yc dA. Okay, so when I can use from 0 again to 1. Okay, so what's going to happen is now, remember the other portion, the other, the element that you are integrating looked like something like this. Okay, here you said the bottom point here is your y1, and then the top here is y2. So the center of gravity would be, the center of mass will be somewhere in the middle here, isn't it?
Yes, sir.
So, but the only way you'll find out is, let's say now, if let's say the height here, the height of this element is, let's say if it's h, if the height is h here, then it means this center should be half of h, isn't it?
Yes, sir.
Yeah, but in this case now, the difference is that the, the distance from there to there now, instead of having something like h, remember we represented it in terms of the difference between this point and this point. So we can say it's difference between y2 minus y1, like we did it before, and y1 like that. Okay, so this point, its middle, the middle point will actually be this point, it will be y2 over minus y1 divided by 2. So the midpoint on that, for that element, the midpoint would be y2 minus y1 divided by 2, which is the same as h over 2. This, we're just trying to find the middle. So that should be now your, in terms of your YC here, because this is the assumed center. So you have not, uh, you can actually you can just add them basically. You don't need to subtract them even. You can actually just add them because you know this point, this exact point already, and this exact point. So you can just add them. Then you find the median of those 2 points. So this should, you should now use that. I think maybe you can use it like that. Isn't it? Yeah, you can just add them. Then you do it like that. Okay. Okay. Then you, okay, this area, when what we did, remember the area that we found here previously, it was the length is this, it was the difference, the length was the difference, y1, y2 minus y1 times this breadth here times d, times d. So you can actually use this also exactly as it is. So here you go, y2, y1, dx, something like that. Okay, so this is all we have to integrate now. Okay, this guy, the half, you can actually bring this half outside. Then you'll be left with 0, 1, y2 plus y1 here. This you can see it from your basic mathematics. Okay, this one you can see they are the same. This one is having a plus and this one is having a minus. You can actually summarize that in terms of y2 squared and minus y subscript 1 squared. You can put it in terms of like that. Something like 1, 0 like that. Then we say y subscript 2 squared. How do we call this rule again?
Is it the difference between two squares?
Yes, yes. You simply make use of that difference between two squares. Because if you don't do it like that, it's gonna complicate you. Like, yo, you're gonna do integration by parts and all. Yo, it's gonna be a long way. Okay, so you still have your half outside. Then inside here, you substitute now. That's the other equations. Then let's check those equations out here. Y2 Y is equal to square root of x. Y is equal to x x squared x squared here is squared because of this, right? Take the bracket here again. Then we have x again here squared. Then like that dx here. Okay. Then we have 1 over 2 here. 2. Okay. This will become just like minus x to the power 4 dx. Okay. So now, question what you, yeah, then you just integrate it the normal way. Here we 1 over 2 here. Here you're going to end up having something like 1 over 2 x should be to the power 2 minus 1 over 5 x to the power 5 to the power 5 1 like that. Okay, once you have that, then this should give you 2 1 over 2 here. Then this will just become 1 over 2. This will just become 1 over 2 here. And then this will just become 1 over 5. Yeah. Then with this
So,
one,
but what happens to the what happens to the x square?
Yeah, you here you substitute. You're gonna replace x with 1. Then you end up having 1 squared.
Yeah.
Because it's like this.
Oh.
X squared. When you are integrating, you're gonna have to
Oh
put.
yeah, and now I'm getting it. Then you minus must also the 1, either 0 square.
Yes, yes. So that will still remain 0. Okay. So with this one, you can put this 1 over 10, or you can just plug it in your calculator. Over 10, 2 goes in 5 times. 5 goes in, yeah, 5 times 1 is 5. 5 goes in 10, 2 times 2 times 1. 1 is 2 here. Okay. So this small portion here will become 3 over. This small portion here will become 3 over 10. So the 3 over it is going to become 3 over 10 times 1 over 2 here. Times 1 over 2. 3 over 10 times 1 over 2. Then this one we're going to have to give you 3 over 20. 3 over 20. Okay, that's 3 over 20. If you plug it in your calculator, 3 divided by 20, that should give you 0 0.15. 0, 1, 5. But I give you 0.15. 0.15. So this top portion, we know it now. So basically, what's going to happen is we know at the top here, at the top you're going to have 3 over 3 over 3 over 20. What we just got now. This dA was equal to, it's the same, it will be the same. But dA to be that still. Divided by dA is 1 over 3. So 3 over 20 times 3 over 1. Again, this is going to give you 9 over 20. Just like here. Again, which is equal to 0.45 again. This is the answer now. So your coordinate in this case will be x in terms of x bar and y bar to be 0 0.45, 0 0.45, 0.45, 0.45. Because remember, these are coordinates that we are trying to find here. Coordinates for the center of gravity. Okay, let's see what we found. This one is for x and for y. Yeah, you see, also got 0.45 units. So this thing, okay, if you look at it here, why is this 0.45? And the x-axis is 0.4 value here. 0.4, 0.45 is somewhere here. Because this the next one is 0. Looks like 0.6 this one. In multiples of 0.2, okay. 0.45 is somewhere here. Again, on the y-axis, 0.45 is somewhere here again. So it's somewhere around here. You can see that maybe, let's say if it's somewhere, if it's somewhere here, you can see maybe it's possible that it's actually the true center. Actually, if you look at it also by yourself, you can actually see that it's almost the same. And again, if you look at this object is more like symmetrical if you look at it. So it must be somewhere in the center because this side and this side must be mirror images for each other. So perhaps this is correct. It should be more or less correct because if the fact that it's giving you exactly the same values for both x-axis and y-axis, yeah. Are you following so far?
Yes, I'm following.
Okay, with this, okay. You want us to go through this one?
Can we maybe do it on another day? If it's okay.
Oh, okay. No, it's fine. Okay, we can always.
It's just because I'm a bit tired.
Oh, yeah. Okay, next time. We can always do it some other times. Okay,
Oh,
so
and they said the quiz would be next week, Wednesday or Thursday.
Wednesday or Friday or Thursday. Wednesday or Thursday.
Yes.
Wednesday or Thursday. Oh, okay. There's still time. We'll see how things go. Then we can always do more. Okay, but at least you understand the concept most.
Yeah, I'm getting it now, but I think I need a little bit practice.
Yes. Practice is the only one.
Something.
Because this mechanics is just like doing is it math? Yeah, I think it's just like doing math. The more you practice, the better you become.
Yeah.
Otherwise, I think you'll be good to go. You just need to do more examples, especially examples that are solved already. Like let's say you find different books, you get the examples that are solved, then you complete them also by yourself. Then you can even do it again and again just to make sure you understand very well.
Yeah.
Okay, then in that case, then have a good night then.
All right. Thank you, sir.
Okay, cool.
I must also have a good night.
Thanks.